It's my pleasure to introduce today's speaker, Professor Marina Blanton. Marina got her PhD actually from Purdue in 2007. I was her advisor when she was here, and it is a pleasure to see her back here. She's going to talk about the general purpose secure computation and outsourcing.
Thank you. Good afternoon, everybody. It's my pleasure to be speaking here today. And I'd like to talk about my work on secure computation and outsourcing. So in some way, this talk is about a project that I have right now, and I would like to mention a couple of different results. So in some way, it's an overview of this research direction. Okay, I'd like to start introducing secure multi-party computation or secure collaborative computation, in which we have two or more parties that have some private information that could be proprietary, could be sensitive, could be private, and I would like to actually protect that information, but they're interested in computing something using it. So the idea behind this computation, in this simple example that I have, we could have Alice and Bob that are interested in computing something on their private data, and the idea behind this type of work is that all of the participants would like to use their computation, their data in computation, but it stays protected. We engage in some computation, but anything that we see looks like garbage, and we're not necessarily can learn anything as a result of this computation. And the only thing that we can know is the result that we agree upon upfront. Okay, so this is similar to the way of just taking our data, sending to some trusted third party that computes everything, gives us back the result, except that there's no such third party that we can trust, so we have to do it ourselves. Okay, so this is the main idea in this work. I've been working this direction, been initiated for a long time ago. It started in the 1980s, and since then there's a great variety of techniques that have been developed. But what I'd like to talk about today is the general purpose aspect of this work, something that what we'd like to do is to use this for any general purpose functionality. And in particular, I mentioned here a couple of examples. Say the first one is, say, DNA testing, when we have two parties. One party say, I would like to have my DNA tested for some genetic condition. I want to know if I'm predisposed to a particular cancer or not. And I know that there's a company that provides the service that extracted some part of genome that tells them what particular pattern corresponds to this condition. But if I just give them my DNA, they know not only where I'm predisposed to this condition, they know what other conditions I might have, they know my family history. It's not just for me. 100 years from now, they still know something about my relatives. So this is not something I wanted to reveal, and they clearly also don't want to, give up their pattern that they extracted because they're making money on it. So in this case, we engage in the computation without revealing the data. All we learn is a part of this interaction, yes or no. Yes, I'm predisposed, or no, I'm not. And another example that I have, when we have actually multiple participants, say hospitals in the area that see some rare condition, they don't have enough data, but if they pull out all of their information together, now they can tell which treatment was more effective or most effective. And obviously by law, they're not allowed to reveal the records, their information, and so the idea is, how can they combine everything together and learn the result without actually giving away their data? So these are all examples of secure computation, and recently we have cloud computing that gave great motivation to this research area. In particular, when we talk about cloud that could take, or cloud computing that could take so many different forms. One example, say, an individual user can use Facebook to manage pictures, for example. I can have a researcher who has a huge amount of data collected from a microscope, and they cannot store this locally, so just pay somebody, some cloud provider, to maintain the data, do backups and stuff. Or even a small company that doesn't have an infrastructure, then would like to pay somebody to manage their data, their infrastructure on their behalf. And clearly, there's a lot of such services available today, and we may want to use them, but in applications that we're talking about, the data is sensitive. So unfortunately, I cannot just take my data that's sensitive and say, oh, please take it, compute something with it. I'll trust you that the data is going to be protected. With the cloud services, first of all, it's I give up control of the data, of the computation, and so I don't know, first of all, if they can abuse my data, if they can look at it and learn something they're not supposed to. For example, if what I'm testing for is this drug effective or not? Learning just one bit of information gives them a huge advantage, right? So I don't want them to learn anything, even just one bit. And another problem is that when the result comes back, I don't necessarily know if I could trust the result or not. I don't know if the computation was performed in the first place or they just gave me some answer. So in some way, in this setting, cryptography is a suite of techniques that will allow us to actually enforce those properties. I can enforce basically data secrecy, and I can also protect confidentiality of the computation or data when it comes back. But so in some way, this served the motivation for the work we're doing. And cloud computing is something that's widely available, but with the secure computation, secure outsourcing techniques, to date, people spend so much effort on sort of certain functionalities, not necessarily general purpose techniques, right? One example would be is that if I optimize computation for comparing two numbers, right? This is widely used everywhere. We compare numbers all the time. So if I make this particular functionality run faster, then I'm affecting so many different programs that somebody might want to use. But unfortunately, to date, most of the computation focused on integer arithmetic, which is clearly not everything, right? If you take a general purpose program, we're working with floating point numbers, strings, there are certain algorithms, there are data structures, that there's much more. Okay, and so in some way, this is something I would like to address. And as a part of this project, we have multiple goals, right? So the first one is I would like to make sure that there's efficient techniques for working with standard data types, such as floating point, strings, different data types that we might want to use in a program. The second goal deals with actual data oblivious algorithms and data structures. So what data oblivious execution means is that when I'm executing a particular program, right, I want all instructions, all commands that I'm executing to be exactly the same every time. It doesn't matter what the data is. And I also want the memory locations that I touch to be independent of the data, okay? So in some way, if I'm taking my functionality, outsourcing it to the cloud, if every time the data or the sequence of instructions are the same, the memory instructions are the same, clearly they cannot learn anything about the data. Let me give an example saying if I'm doing binary search, right? If I have a sorted set and binary search can give me the result very quickly, but I have to access locations that depend on my data I'm searching for. And over time, if the cloud sees a lot of these queries, they know what I'm searching for. They know if I'm searching for the same item as last time, if I'm searching for something else. And the idea is that we don't want them to know that. We want them to execute the task, and that's it. Know nothing about the data that I have or a particular task that I'm running. So the idea behind sort of this data obliviousness is we take an existing algorithm or data structure, most of which don't have this property. Some of them do, but most of them don't. And we would like to see how can we take this algorithm, make it data oblivious at the smallest possible cost. Okay, there will be an extra cost that we'll need to add to our algorithm. It's going to be a little bit slower, but the idea that it's just going to be a little bit slower, not much slower. Right? As a trivial example, if we turn binary search into a linear scan, when I touch all of the records, this is clearly so much worse than in most settings. This is not acceptable. Okay? And normally data oblivious techniques enforce this by not touching exactly the same locations every time. Normally they're randomized, so you're touching sort of locations at the same distribution, but different every time because it's randomized. And the last part of this project is building a compiler that basically takes a program that's written in a conventional programming language. Say we chose C because of its popularity, and then it takes this program if you see a variable and you'd like to protect data that this variable contains, you're saying this is private, this is sensitive, this is proprietary, you'll just mark the data type as private. Okay, so now we distinguish between public and private. We have two sort of qualifiers for every variable, and if you say it's private, our compiler is gonna take this variable every time we compute on it. It's gonna change the operations that are being done on that variable and transform it into secure computation techniques. If the variable is public, there's nothing changes. We don't change anything. And so the idea is to basically build this source-to-source compiler that takes the source, produces a different source, and this the result will be the program that can be securely run in a variety of different settings, whether this is outsourcing, whether this is secure collaborative computation, and it's actually suits a lot of different settings. Okay, so these are directions that I would like to talk for the rest of this presentation. And I wanted to mention just a couple of techniques that we so far developed. So the first one that I would like to talk about today is private floating point arithmetic. Basically, I like to describe how we compute on floating point numbers for the first time in a secure setting. And I've also talked about set operations, which are common in general purpose programs. And in particular, the idea here is that we wanted them to be oblivious. We wanted to be them data oblivious, which in prior literature was not the case. Another topic that we worked on was data oblivious graph algorithms, but actually I'm not going to include them in this talk, and the idea was the same, that we wanted to make sure that the algorithms are oblivious, independent of the data. And the last part of this project and this talk will be focused on the compiler. I would like just to take to say a little bit more about what we did and how we implemented it and what we thought was suitable for the setting we're working in. Okay. So I would like just to give sort of an introduction or description of the setting in which we're working, and everything that follows will be in exactly the same setting. And the setting works either for secure sort of interactive computation and also works for outsourcing when we're using multiple servers. Okay. So in general, if we talk about secure computation, there could be a variety of different techniques. Some of them work for certain settings, some others work for others, or could be the same. And in general, we can distinguish between secret sharing, homomorphic encryption. We can distinguish also, we can use garble sorting techniques. But for this particular project, we relied on linear secret sharing scheme. Okay, so that there's advantages to using it and those are that it actually provides information theoretic security, meaning that doesn't matter how much computational power I have, I don't just have enough information whatsoever to know what the secret was. With encryption, if I encrypt with traditional techniques, that there is a certain time limit, I can brute search for the key and eventually I'll find one given enough time. Here, this is not true. Given an infinite amount of time, that there is just not enough certainty to help us to know what the secret was, right? So it holds unconditionally. And another advantage of this is that it doesn't use cryptographic techniques that are expensive. And for example, with information theoretic setting, you can use numbers that are of the same size as those that are dealing with. With encryption, often you have to make the numbers much larger to guarantee security of the encryption scheme. Okay, and so in our setting with the linear secret sharing scheme, we assume that each value, which is private or secret, will be split into multiple shares. And if you look at the shares, they all look random to you. And even if you combine some of them, they still are going to look random unless you combine enough. Okay, so that this threshold, so we call it NC, threshold linear secret sharing, where N stands for the total number of shares, and C as the number of shares that's the maximum that doesn't give you the secret. T plus 1 is required to reconstruct the secret. T is still not enough. So if we say, if I take a secret, split it into 5 pieces, and I require 3 or more parties to get together in order to reconstruct it, then this would be the number of parties 5, and the number of, and the value of T is going to be 2, because 2 still cannot do anything in the setting. And so it's called linear secret sharing for the reason that if I have the shares in this representation, then I can apply any linear combination to the values in secret sharing form without actually having to interact with anybody. I can add 2 shares locally, I can multiply them by a constant, or any linear combination can be done in this way. But multiplication here will require interaction of the participants, so they have to interact, and this multiplication in some way is counted as the sort of minimal building block that's interactive. And so the cost of this technique comes from the fact that the participants have to interact, right? So when we measure the overhead of the solution normally, because the techniques themselves are not expensive, we measure it in terms of the number of interactive operations, okay? So say you have to interact 20 times or 100 times. And also what's important for these techniques is that there's certain overhead. If I have to send the data, receive it, do this again, that there's another metric that's called rounds. Rounds are sequential operations, sequential interactive operations. So if I have some operations, if I have to compute 100 of them, but they can be done in one round, I just send you 100 shares, I wait for 100 from you, and that's it. As opposed to be doing one at a time, which is clearly going to take more time. So round complexity is also crucial. And some people may say that even this is the most important factor that will determine how long your program runs. But what we try to do, we try to balance. We try to balance the overall work and the number of rounds for a protocol. Okay. And so in this setting, we take all participants and we divide them in 3 groups. Okay. So we know that there will need to be some computational parties that actually run the computation, but we also say that there will be a group of input owners, those parties who actually have the input. It could be a single client, it could be 100 hospitals, it could be basically any number of users. And then we'll also say that these input providers will just take their data, split into shares, and send it to the computational parties. Computational parties run the computation and provide the output to the output parties, who once again could be completely different from input or computational parties. They could be similar, they could be overlapping. There are no requirements whatsoever between these 3 groups. Right? They can be completely arbitrary, which makes this suitable for outsourcing. When we have a client who sends the data to multiple servers, it could be that 100 hospitals choose 5 of them to run the computation on their behalf. It's possible that we have 2 participants who are going to employ a third party to do it together in this setting. So it covers a large variety of different scenarios, and it works for any of them. So I'll say that what we're developing is suitable for either multi-party computation or outsourcing, where you're using multiple servers to outsource your task to. Okay. And so the first result that I want to talk about deals with floating point arithmetic. So this was a paper that was published in NDSS last year, 2013. So if you're interested in more details, you're welcome to find out more, because this is sort of just an overview talk. I won't be able to go into too much detail. But with floating point arithmetic, they're actually very important for a lot of engineering tasks, for financial tasks, for scientific tasks. And in some way, we're looking at that and saying, when you actually want good precision, this is the best possible representation of numeric data. And we design a suite of different techniques for working with a floating point, with numbers and floating point representation. So in general, we know that secure computation is possible for any function you might want to do. But the challenge every time is to make sure that we can do it faster than what was available before, right? How can we create the solution that is going to have reasonable performance? Because normally when we take this to secure context, it becomes quite a bit more expensive, okay, in terms of the computation that we need to do. So the challenge this time was to ensure that the run complexity is small, and we also wanted to minimize the overall computation, the overall runtime. And generally, with these techniques, if we're talking about operations on floating point numbers, and you can call a million operations on floating point numbers, right? So we want each of them to be quick, because we don't know how many times the application will need to run it, and it's the best if the number of rounds is actually constant. If we can say it runs in 5 rounds, 10 rounds, as opposed to depend on how long the number is, okay? And but it also, if the constant round comes at the cost of huge total work, that this is not something we're interested in pursuing. So we're looking at a balance. And actually, constant round protocols was something that was a direction of research in the last few years for integer arithmetic, so that there is some background that was developed, just not for this data type. Okay. So it's kind of interesting designing solutions in this framework. And the most interesting aspect that this is completely different from any other setting that you might want to pursue. Right? With traditional architecture, say any computer that you might work with, we know that multiplication is going to be, say, quite a bit more expensive than comparisons than additions. In our setting, with the linear secret sharing, all additions are basically free. They're local, they're quick, as opposed to those operations where you have to interact. So multiplication is quite a bit more than addition. Addition is basically free. But comparison is quite a bit more than multiplication, right? So if you're in this setting where it doesn't actually line up with traditional architectures, you have to look and see how can we minimize the number of comparisons. Say we can afford a lot of multiplications for the cost of one comparison, but this is, puts aspect of optimization in a completely different perspective. And this is something that's interesting for working in this particular framework. So what we built in the setting, we provide all sort of basic operations such as floating point addition, multiplication. We do division and subtraction, the same as addition. Then we did some conversion between integer and floating point data types. And we also looked at some of the more complicated operations, such as computing log, computing a square root, and exponentiation. So those would be calling floating point basic operations, and those will be quite a bit slower. And so also the way we approach this, right? Say we have floating point, and the way floating point is represented, say we take any number, right? It could be huge, it could be very tiny, and then with floating point representation, we normalize it so that we have a fixed number of bits for the significant, and these are the bits that are meaningful. It's not like we might have a huge number of zeros in front of it and only a really tiny fractional part, but we don't actually need to represent the zeros, right? We need to represent the meaningful part of floating point. And so then we also use the exponent that says how the significant should be shifted up or down, right? We use the power. We actually use the power of 2. And so with these values, if you want to add two numbers that are presented in this form, you have two representations, two significance, but we need to align them. If we want to add them together, we need to know where they stand with respect to each other, right? each value is represented in normalized form, meaning that the most significant bit is 1, to make sure that we can work in them in this form. And so we capture a certain number of the bits. We know we're guaranteed to capture a certain number of bits that are meaningful. And so then if we implement something like addition, that we may need to compare certain values, align them, perform subtraction, and then need to normalize the value as well. So addition is actually something that's more complicated than multiplication and floating point. And this is not only for us. This is, in traditional architecture, it's the same. Multiplication is easy. You multiply two significants and adjust the powers. I mean, there's there's not a lot to do, but with addition, you first have to align them. And this is how our addition looks like. And it's actually didn't fit a little bit, that there's a few lines that didn't fit on the screen. But the idea that I would like to demonstrate is not necessarily for you to understand what this is saying, it's just to show how we actually want to implement this logic. So in our representation, each floating point number is represented by 4 different components, 4 fields. We have significant, which is the value itself, we call it V, and then exponent, which is P in this case, and we store 2 more bits. We store the sign bit and we store a 0 bit, because for a 0 bit there's no normalized representation in this particular setting. Okay, so if you look at this algorithm, the idea is that every time we run it, it has to execute exactly the same instructions. If one number is bigger or the second number is bigger, it has to look identical every single time. So in some way, the if statements are encoded in this fashion that I first evaluate the condition and then execute the if statement and else statement, and depending on the result of the comparison, I use either the first or the second. But you always have to execute both branches of the if statement, or if there's only one, I execute the if branch and I keep the previous value in case I need to go back to the original value if the loop or if the if statement should not be executed. But if you look at this, we have this square brackets that actually mean that the value is protected. So we perform some comparisons to see which exponent is bigger, which significant is larger. We keep track of the maximum minimum, then we align them and normalize at the end to make sure that's in the same representation that what we started from. Okay. Well, this is just an example. This is not for you to actually understand the details of this algorithm, because I said addition is not the easiest from all of the separations that we've done. Okay. So what I wanted to show you is the results of our experiments. We implemented this on with 3 computational parties. So the secret sharing is used 3. One value is split into 3 shares, and 2 of them need to get together to reconstruct the value, 2 or more. And if you look at this result, we compare it to integer, fixed point, and floating point arithmetic. The first one, I believe, the first one is addition. The one on the left is addition. And if you can see, integer and fixed point are so much faster than anything that we do. And this is expected. It's expected because in the other 2 representations, they're local. You just add local and that's it. You don't have to do anything. So this is a logarithmic scale that says we actually take a couple of milliseconds to run this operation, and addition in our case is going to be slower than multiplication. This is expected. But then if you look at the next one, the one on the right, this corresponds to multiplication. And now for us and for integer fixed point representation, the numbers are very similar. And I think, right, so fixed point and floating point are very similar. This is still logarithmic scale because for integer operations, it's basically one interactive operation. For 2 others, that there's a need to actually truncate the value, and this is where the main cost comes. Because you multiply 2 values, then you need to truncate them. But you still see that this is on the order of a couple of milliseconds. And so the way these graphs are shown is that we run a number of operations together in a single batch. say if I can perform 10 operations in a single round, 100 operations in a single round, or 1,000, this is what you would see. And it's clear that if you do only one or a few, then per operation the cost is going to be higher than if you can execute 100 of them together. And depending on the application, you may be able to do 100 together, or it's possible that you're forced to do one at a time. Okay, and so this round complexity is also something that we try to address with our compiler. We try to minimize it as much as possible. And the next two plots are for division and comparison. So if you look at the division operation, in some way this is the costliest across all of the four that we looked at. And if you see that floating point is actually the best, okay? This time, this is something that we didn't necessarily expect, that for integer and fixed point, they're going to be slower. And this time, the scale is not exponential, so that this is not a huge gap. But still, a couple of times it can be significant, right? And the way we actually can achieve this faster is because we could use for this experiments, for this comparison, we could use shorter representation. With fixed point, we'll say if we use 32 bits before the period and 32 bits after, that's already 64 in our case, because you don't know where the significant or where the meaningful bits can appear. In our case, we use slightly shorter representation, and this is why it was faster, while we're covering a much larger range of different values. Okay, and so with the comparison, you see that the results are also similar. Because all of them, whether this is integer or fixed point or floating point, I would call integer operation in some form. And so you'll see that their performance of all of them are comparable. All right, and the last two is performance of floating point logarithm and exponentiation, and there's nothing was available in the literature for other data types, so we didn't implement those. And as you can see in here, as that the performance is, I would say, on the order of 100 milliseconds, which is not the fastest, but it's actually pretty good for secure computation and for that type of operation, which is pretty complex. Okay. Are there any questions about this at this point? I'd like to proceed with the next topic. So if I switch, yeah.
So in your exponentiation operation, are you performing this operation on two protected values?
So what we're doing, we're actually raising 2 into a floating point number. Okay. So 2 is known, but it doesn't necessarily help you much. The exponent is the one that has to be converted in the proper form, and the size of the numbers is what is going to be the main complexity factor in this case.
Okay, thank you.
And well, in general, we chose 2 to be raised in certain power because you can always change the base. You can always convert it to another base. All right, so you did have a
Are there any other frameworks that support, that are based on linear secret sharing schemes such as ShareMind? Did you compare?
Right. Yeah, this is something I'm going to talk about at the end, how our compiler compares to ShareMind. ShareMind is actually very interesting because it uses somewhat similar secret sharing, but it's non-standard. But it was optimized very much to work well. They actually been working on it for a number of years now, and it was surprising to us that there's many operations were actually quite a bit faster. But I'll talk about it at the end when I talk about the compiler. Okay. So the next part is deals with secure set operations, and the important part here is that we wanted to implement data oblivious operations. And once again, the idea is that if 2 operations are being outsourced somewhere, that you, with what was available before is that normally it was a 2-party set operation, not often set intersection. One party has a set, another party has a set, and I like to know what elements are in common in those 2 sets. But there's pretty much all solutions that are available, they assume that you know one of the sets. And so the correctness of the result that you recovered depends on you knowing what the set was. Okay, if you don't know the set, you cannot compute the result correctly. Okay, and so even if you do some sort of multi-party set intersection, you still had to know one of them, right, to be able to compute this correctly. So this is clearly in the outsourced setting. We don't want the servers to know what the data is, so we don't want them to run those types of algorithms. And also, if the set operation is not the entire computation, if you have to do one operation then another, they're not gonna be composable in the sense that you have to know the intermediate results in those cases. You cannot just combine them together into a bigger computation. You have to use just one operation. So what we've looked at is designing this algorithms for set operations and multi-set operations. And in particular, we wanted them to be data oblivious. Okay? So the idea behind this is not necessarily very complicated. So we looked at, say, if you have a set, right? And then if you have another set, in some fashion, you want to be able to compare all of those elements in one set to all other elements in that set. So if, say, if suppose that they're sorted, right? If I compare them one by one, if I have the first one as actually the larger than everything in the second set. So it means that even I have to compare the first one to the last, to the first, to all of them, right? And the same thing for the last set. So in some way, I have to compare all pairs of these elements. If I don't know anything about the sets, but if I in some way didn't have to do that many computation, means that I knew something about the sets and I could skip some of the operations. But what was interesting in our setting is that, well, this if the sets are size n, that those n squared comparisons are not required if you can actually do some operations, some comparisons, and deduce something about others based on the result of this comparison. So what I'm saying is that some of the comparisons can be implicit so that you don't have to do that, right? And so what we actually implement is we implement our solutions that use n log n comparisons when n is the total size of the sets. And they're oblivious. So this is not necessarily as good as what's available in the two-party setting, where I know the set, but this is actually works pretty well. This can be used in a variety of other settings that just individual operations cannot be used. So the main idea is, actually the high-level idea is pretty simple. So what we take is we have, suppose we have two input sets, right? We sort each of those individually, and then basically what we do, we're gonna put them together. So we're gonna take two sets, put them together, and sort the result, okay? So if this is a set, meaning that an element in my set would not be appearing twice or more. It's gonna appear only once. So I have this combined set that's been sorted, then I can look to all of the adjacent elements in the set. If two of them are the same, right, that I can compute the result of some operation on them. Saying if I'm computing the intersection, if two adjacent elements are the same, that I actually going to erase one of them, keep only one that's going to be in the intersection. If two adjacent elements are different, I'm going to erase both of those because they're not going to be in the intersection. Okay, by just looking at the results, scanning it, I do one scan, comparing adjacent elements, and then I'll know what the output is. Okay, so this actually requires using sorting algorithm that's also data oblivious. Okay, otherwise this is not going to work. And fortunately, that there's recent work that some of those techniques were developed recently with n-log n time. Before that, it was quite a bit more. Well, I guess it was n-log squared n for practical algorithm. And so in some way, this helped us to have the complexity that we claim. And so this is the main idea. We can do similarly, say, set union we can do set difference, we can do pretty much any set operation that we want. We can do a subset relationship between two different sets, and the same idea is going to remain, that we combine two sets together, or even more than two, scan them, sort them and scan them looking at adjacent elements. If we combine more than two, then we look at elements in a number of positions apart, depending on how many input sets we have. So the main challenge that we needed to address as a part of this work is the fast round complexity. Right? So if you look at the set, if you compare two of them at a time sequentially, if your set contains 100,000 items, right? This is, that's a huge number of comparisons that have to be one after another. It's going to be long runtime. In our case, for certain operations, your decision would be based not on just one comparison, and a couple of comparisons. So we want to make sure that all of those operations that we do can be processed in parallel. That we do all those comparisons all together and just construct the result, where the resulting set is, all of the elements are computed in parallel. Okay? And then basically the idea here is that we either keep an element or erase it. And so we don't necessarily change the size of the output, and this is the time where you can also protect it. You don't even have to reveal the size of the resulting set. But if you do, you'll need to drop all of the zeros from the result, and then you know the size. Okay. What was actually more difficult for this particular work is designing solutions with small round complexity for multisets. Okay, so with a set, if the element appears once, then you basically need to look at two adjacent elements and you're done. With a multiset, one element can appear any number of times, right? So if you just put two elements together, if you're doing something like set intersection, and suppose that the same element appeared 3 times in both of those sets, then you'll need to keep 3 of those elements. But you cannot necessarily just take the previous techniques and apply in this case, because the result is going to be wrong. Okay, so we have to modify it, and if you actually, the idea that we had was, we take a multiset and convert it into a set representation, and then everything that we developed before could be applied to the new representation. And so the representation was that we basically number the number of instances for the same element, so it appears 5 times. We'll just have multiple indices, okay? And then now each element is a pair, is the value and the index, and we basically can apply the previous algorithm because all elements are distinct. But the idea was that we developed an algorithm that runs in constant round and then produces the numbering for all elements in parallel. Okay, so I won't be able to go into a lot of details, but this is something that I want to mention, is that this was in some way the most interesting part of the work, that how to design an algorithm that minimizes the round complexity, that we can actually produce this numbering, these algorithms in the same time. So the bottleneck of all of our solutions is the sorting. Okay, past sorting, we have basically constant round complexity, and the overall work is linear in the size of the set. So the sorting will be the most expensive step. And so this work was published at Asia CCS in last year, 2013. So if you'd like to look at more detail, then this is where I would direct you. Okay, so this is just one plot that shows the performance of our techniques. And basically what it shows, that say if you have 2 sets that are 1,000 elements each, that it's going to take you on the order of 10-15 seconds to do the intersection, which is actually pretty good for secure multi-party computation techniques. And here I listed two different curves. One says this is with compaction and the other is without compaction. And what this means is that compaction is basically a more efficient way to basically, we use compaction for the reason when the output should be opened. So if I perform a particular algorithm or a particular set operation and I open the result, the position of the zeros will tell me something about the input. Okay, so we cannot just open, we have to somehow randomly shuffle the values or sort them, or what we do is we do compaction. In compaction, we'll take a set, put all non-zero elements first, followed by all zeros. So when we open it, that doesn't tell us anything about the inputs, just the result, and it's faster than doing the sort of full sorting in this case. So as you see, the cost is actually pretty small compared to the rest of the algorithm for doing compaction. Okay. And so the last part of this talk, I'd like to talk about our compiler. And this is the newest from all the work that we've done. We're actually still working on the compiler, but this particular result was published in CCS last year. So once again, if you're interested in learning more, I will encourage you to look at this. And the idea here was that we had this sort of vision of taking a general purpose program and convert it into something that can be run in the outsourced setting, in an untrusted setting, right? And as I mentioned before, most of the available techniques were for integer arithmetic, and we wanted just to say whatever the programmer is going to write. We'd like to take this and convert it into a secure implementation automatically, so that you don't have to be an expert, in this area. I mean, to some extent, you still need to understand how this tool works, but you don't have to actually implement this from scratch, right? So we chose the C programming language. At this time, we implement all the features of C except pointers. So basically, pointers actually make this not only more complex, they make some of the features impossible to verify, right? But this is, still our intent to extend this to a sort of broader version of C. Basically, the main difference will be is that when you write a program, for each variable, you have to mark it as either private or public. If you don't mark it, we assume it's private, because we don't want some sensitive information to be leaked by accident, right? So we're doing everything on the conservative side, so if somebody makes a mistake, it's going to be the more secure version, or it's not going to compile, right, if somebody makes a mistake. So also, for performance reasons, we'll make the data types to be variable and bit sizes. So say instead of using regular 32, 64 bit integers, for example, say if you declare it to be 15 bits, that's going to run faster. Okay, and so we allow this possibility for all variables, for numeric variables, to be declared to be of a particular size. It's the same thing for floating point. You can specify the significant, the size of the significant, and the size of the exponent that you want to use. Okay, so our compiler takes a C program, compiles it into a C program, and we chose it because we thought, if we compile it to the code, we don't necessarily want to implement all of the optimizations that compilers already do. We're going to produce a C code, and then you're going to compile it with your native compiler on the computer that you already have, right? So if you look at the first diagram, that shows how a user or a number of users will take their program and compile using our tools, right? So what you need to input is your program specification, right? The program, and you also need to provide certain setup parameters. What kind of or what are the parameters for the secret sharing that you'd like to use? You'd like to split in 5 shares or in 10. And also, there could be some other setups in terms of the security aspect of the computation, right? And so when you compile it, you just give it to the machine who's going to run it. They compile it into the binary on their own server. And so the image on the right-hand side shows the sort of the process that is performed at the execution time. So we see that, I don't know if you can read this well, but what the user does, the user takes the input and runs the small program that is going to produce shares of the variables that are called from that program, right? And so then I ship shares of my variables to one server, then the other set of shares to the other server. I send it to all of them, and then once they receive it, they'll start computing on basically on the shares that they respectively have. And at the end of the day, once the computation is done, they'll send their shares to the to the output parties who are entitled receiving the result. Okay, and then also once I have the shares, I run this small program that is going to reconstruct the output. So nobody knows the output except the person who receives the shares. And so in all of the interaction is encrypted, is on encrypted data, just using regular AES, the encryption standard, to make sure that each share should be communicated to only one party, not visible to everybody. Okay, and so I wanted to say just a little bit more about optimizations that we performed on this compiler. And that primarily deals with sort of minimizing the runtime, the complexity, the run complexity of this algorithm. Okay, so in general, we're not the first, to approach this sort of compiler paradigm to secure computation. Right, there are some compilers that are already available, but in some way we saw extremes. So if we look at something like that's called VIF, so with that implementation, what happened is that they try to parallelize as much as possible. So they call for every minimal operation. They'll say, "We'll parallelize it as possible," but if the instruction cannot be executed, if the two inputs or how many inputs it may have are not available, the operation is blocked. But everything is created, there's a thread created to every elementary operation, just in case it can be parallelized. So that actually gave pretty poor performance because often there's no need for that many threads, and it just was an additional overhead. There are some others that actually don't do as much. Something like was brought up, ShareMind has only parallelization at the level of arrays. So if you have two operations that you need to be done many times, say you need to do multiplications on a large array. So you need to multiply, you provide two arrays, you multiply them elements-wise, but if you cannot represent your computation as an array or matrix, that's it. There's no parallelism, in any other form. So what I wanted to do is to be somewhere in the middle. Right? We're not as expressive as VIF, which was so slow, and give more flexibility to the user to actually, if they know that they can parallelize parts of the code, they could. So the idea is that we also implement this parallelization, or we should call it, it's not necessarily parallel execution, in some it's batch execution. We still execute all of the operations, but we execute them in one batch. We send, 100 shares, receive 100 shares if you can do 100 operations at the same time. But we also say we provide loops. If you know that there's a certain for loop where all of the iterations are independent, then you can put a certain syntax, in our case that's square brackets. Instead of curly brackets, you put square brackets, and that will tell us just run all of those iterations together. Right? And the last part where we also say there could be certain cases when two parts can be run in parallel, but they're completely different. They're not related, like in a loop. So say you can also specify that this part of the code and this part of the code can be run together, right? Well, then we create completely separate threads and we execute those tasks together, right? And so this is probably just my final slide that shows the performance. And so we called our compiler Pico. and also show ShareMind. In our paper, we compared to another compiler for C for two-party, but so what was interesting to us is that ShareMind was actually optimized for a particular setting. They have to have 3 parties. They cannot work with more than 3. This is in some way drawback of their setting, but in some way what was interesting is that for small operations we do so much faster, right? If you look at something like even the first experiment that we ran, 100 arithmetic operations, they are run in actually together, right? So on the LAN, it's clearly the round trip time is so short, so you can do it well under a millisecond. For some reason, ShareMind takes a lot of time to start, but after they invested in that initial cost, then each operation on top of it is basically very quick, right? So they're really optimized for this massive parallel execution. But what we wanted is to have a general purpose program, and a lot of computations are sequential, right? We try to sort of strike the middle. We try to optimize it for parallel execution, but also, try to link the fastest building blocks if the program is sequential. So if you look at this, some of the more complex experiments that we've done, more of the complex functionalities here would be something like fingerprint matching that still is quite a bit faster for us on the LAN, but for a WAN, wide area network, they're comparable for us and ShareMind. But in general, if you have a program that's parallelizable, it's going to be quick, even if the size of it is large. For example, like matrix multiplication that we do 20 by 20, this is actually 8,000 multiplications that you have to do, and it's done in a matter of 2 milliseconds on the LAN. So this is clearly pretty good performance for secure computation techniques. Okay, so this is all that I wanted to talk about today, and in some way, this project is still ongoing. We're still going to look more at data oblivious execution. In some way, this is interesting. There hasn't been a lot of work, right, in this direction, and I see a lot of potential looking at a lot of different algorithms, even something like a search. It's not clear how to do this obliviously in a fast fashion, right? And so I think if you're interested in this research direction, I think there's a lot of potential. Right? So I would like to conclude here, and I'll take your questions this time.
Thank the speaker. I think we have time for a brief question. I have questions, but I think I will ask them privately. This is about privacy, so. Thank you very much. Yes, thank you.